Hello everyone. In this video, I'm going to explain you the solvent effect on U visible spectrum. Consider a typical U visible spectrum for a molecule. You will get wavelength lambda in nanometer in x-axis and the intensity in the y-axis. It is nothing but the optical density or the absorption of radiation. We will be normally recording between 200 nanometer and 800 nanometer UV in the visible region. If you see the typical UV visible spectrum, that will have band like this represents the lambda max. The intensity at the maximum intensity at particular wavelength called as lambda max. Right? This is due to sigma to sigma star transition or pi to pi star transition, n to pi star transition, n to sigma star transition, all this. It depends on what kind of chromophore it contains, the molecule contains. According to Beer-Lambert's law, the concentration of the medium will influence on the absorption. When the concentration of the medium increases, the absorption increases. We will be analyzing the transmittance at last by considering the intensity of incident radiation, the intensity of the transmitted radiation, we can able to calculate the intensity of absorbed radiation. We know that if the concentration exceeds, then the absorption increases, but at particular concentration, above particular concentration, that the amount of molecule, the number of molecule present in between, I mean within the path length, consider this is what the container, you have some molecule like this. When the light with I naught is passed through, it will be passing through some of the molecule present here. If the concentration increases, the number of molecules that is coming in between will get increased, so that there will be more reflection happens. Then the transmitted radiation will not be reflecting the absorption at all, because in this case we are not considering the reflected radiation at all. We are considering the reflected radiation of 0, and by using only the transmitted radiation we are calculating the absorbed radiation. Then the reflected radiation will also be considered the absorbed radiation. There we will end up with the error. So the concentration should be restricted here. It cannot be like even more than the saturated level it can give us the lambda max value. No, there is a restriction. So always what we do, we will be using diluted solution to record the UV visible spectrum. For the dilution we will be using kind of solvent. So there are polar solvent and non-polar solvent we are using. Polar and non-polar solvent. Always we prefer non-polar solvent in the case of recording UV visible spectrum, because we don't want any kind of interaction between solvent and the solute. If there is a polar solvent, for example, then the polar solvent has the dipolar moment. That dipolarity will be interacting with the solute. That will lead to the change in the absorption, either change in the intensity or change in the wavelength. Right? Let us see how it changes the wavelength. There are two cases we can take. One is the n to pi star transition, another one is pi to pi star transition. In the case of n to pi star transition, n is the non-bonding electron. Oxygen will have 2 lone pairs, nitrogen has 1 lone pair, sulfur will have 2 lone pairs. Right? These are lone pair of electron present. Right? It is called non-bonding electrons. If you consider oxygen contains 8 electrons. 1 has 2, 2 is, it is 2n square rule. The first one, 1 has square, 1 has 2, 2 is 2, 2p4. It is through 2n square rule, the electrons will be filled within the atom. So there is a nucleus, neutron and the protons. and then first orbital, if you substitute 1 in n, it will be 2 electrons. So 2 electrons will be filling the first orbital, and next orbital 2 into 2 4, 4 into 2 8. So 8 electrons can be filled, but there are only 6 electrons left, so 6 electron will be filled. 4 5 6. Now the valence for oxygen is 2, so 2 electrons will be involving in bonding, right, and other 4 electrons will be there as non-bonding electrons. That's why when you mention always oxygen, 2 pairs of electron you will be mentioning at top and bottom. It represents the presence of non-bonding electrons. For nitrogen, sulfur also there will be non-bonding electrons, right. So if the molecule contains oxygen, sulfur, oxygen kind, the nitrogen kind of elements, then there is the possibility of getting N to pi star transition. It absorbs energy as the non-bonding electron will get excited to the pi star level, right. So considering only N to pi star transition, the polarity increases the energy, because the electron in the non-bonding electrons will be highly stable at the ground level. If it is highly stable at the ground level, it needs more energy for the absorption to get into excited level, which is unstable, which is normally unstable. See, normally it doesn't get into unstable state. It wants to be always stable. As the ground level is highly stable in the normal condition, we need more energy to take the electron from the N to pi star, right. So in the case of N to pi star, this is N and this is pi star. N to pi star, when the polarity increases, there will be increase in the energy. Right. Let us consider this is delta E1, delta E2, delta E3, increasing polarity. Energy delta E3 is greater than delta E2, greater than delta E1. Because the non-bonding electrons, the electron present in the N state is highly stable when the polarity increases. As it is highly stable, it doesn't want to get into excited state, so that you need more energy to get it excited. Clear? So the wavelength will be shifted when the polarity increases, wavelength will be shifted towards the blue region. So there will be blue shift. So considering N to pi star transition, as the electron present in N state is highly stable when the polarity increases, you need more energy to excite the N electron to pi star level, so that the wavelength will be shifted towards the blue region. It is called blue shift. Okay, when the polarity increases, there will be blue shift in the case of N to pi star. If we consider pi to pi star transition, the excited level is highly stable when the polarity increases. Considering a pi electron, the electron present in the pi state, it will absorb energy at particular radiation, it gets into pi star level. When the polarity increases, as the pi star electrons is highly stable, it needs very less energy to get excited, right. Consider this pi to pi star transition, the energy you are giving delta E1, in the other case you are sending delta E2, pi to pi star, and delta E3, pi to pi star. Now delta E3 is lesser than delta E2, lesser than delta E1. It means there is a red shift. When the polarity increases, considering pi to pi star transition, there will be red shift. The wavelength gets shifted towards the red region. Clear? I will give you an example. Okay, this is a molecule we are taking, sorry, it is a acetone molecule, double bond O, right. Now in this there are non-bonding electrons here, there are pi electrons here, right. So there will be n to pi star transition as well as pi to pi star transition. Considering only pi to pi star transition, first, when you are increasing the polarity, initially I am taking hexane and then diethyl ether and then next ethanol, methanol and water. The polarity increases from hexane to water. Water has a high polarity, right. So when the polarity increases, if you see the wavelength, excitation wavelength, initially it is at 229, 230, for ethanol it is 237, for methanol it is 238, for water it is 244, right. It gets shifted towards the red region. I mean red shift happens here. Red shift happens here. It means energy gets reduced because the electron is highly stable in the pi star state. It needs less energy. That's why wavelength gets shifted towards the longer wavelength. Why is it so? Because if you see, the polarity increases the interaction. Polarity means it will lead to dipole-dipole interaction. It will lead to kind of hydrogen bonding based interaction, electrostatic interactions, van der Waals forces. So interaction gets increased when the polarity increases. When the interaction gets increased, it will tend to interact with the pi electrons there, so that the electron in the pi state is highly unstable. So that always it wants to be stable. By gaining the energy, it will get into pi star excited level, right. So low energy itself, it can absorb energy, it can get into high excited level, which is a highly stable state, right. In the case of n to pi star state, if you see, same hexane, it shows 327 nanometer, and then diethyl ether it shows 326, and it gets decreased 325 until 305 it goes for water. See, wavelength gets shifted towards the shorter wavelength. There is increase in the energy because in the n to pi star, the electron is highly stable at n state. It wants to be always paired. Okay, so this is the reason why we get shift in the presence of different solvents. It is because of polarity. Okay, thank you.